Good afternoon, I'm Jade and this is Oliver, so you already kind of know a little bit more about us. And today we're here to present our research and subsequent development of a new building asset that we have named Behavioural Skins. So quickly,
There we go. No? I guess, okay.
As a quick intro, we are primarily architects, focusing on the future-proof solutions, particularly how we are approaching the method of tools towards design. And this is a small overview of the work that we're doing, ranging from sculptural projects to interactive music installations, architectural proposals, as well as teaching with both ties to the Angewandte and University of Innsbruck.
At the start of the project, we ask ourselves, what is sustainable architecture and how does the world perceive it? According to current text-to-image AI tools, this is sustainable architecture, a mix of greenwashing elements disguising a mass of glass and concrete, which remain unsustainable no matter how much greenery and solar panels we add to them.
So Behavioural Skins tries to challenge this perception through developing a holistic approach and system to location, design, material, and implementation. Buildings have been around for thousands of years, as we already know, and as our cities grow, some of our older buildings become unfit for our current standards. The project takes place in Vienna, or our first sort of initial thoughts focus around the city, where there are an abundance of Grunderzeit buildings that are left vacant, and they're constructed mostly of thick brick walls with a surplus of materials and offer good spatial qualities like high ceilings and adjustable floor plans, so they can be used for almost any city function. These buildings, if adapted, could be used to house the growing population affordably and sustainably. As we grapple with climate change, finding cool spots in the city also becomes increasingly more difficult, so these would potentially house people
in the near future.
Yeah.
To allocate where intervention could have the biggest impact on the city, we developed a tool that uses open source climate and housing data, which we've tested on this crop-specific site in Vienna. It's in the 15th district, close to the one of the main subway stations. Our remap script visualizes zones from heat islands to cold air streams using advanced computational workflows and categorizing them into distinct color clusters. These range from blue, indicating cold air streams, to red, signifying intense heat island conditions. It details building developments, differentiating between structures from the Grunderzeit era and others. All these data points converge to empower users with a comprehensive, individualized search experience, and this then also allows for precise and straightforward identification of intersections between heat islands and abundant Grunderzeit buildings. The method of how we approach the design is through developing a building asset via human and machine co-creation. Essentially, a brick-like building component that spans the width of an existing wall. The procedural workflow begins by identifying the masses that need to be replaced in the existing facades, and then decodes this volume, dissecting into a three-dimensional grid, where the perimeter of the grid is 0.3 centimeters to ensure a stable fabrication process. The vertices on the cuboid's 6 outer surfaces are then connected with the longest path to inform the maximum surface area and achieve a multi-connecting groove characteristics. The length of the curves directly corresponds to a specific wall situation, and the porosity of the mass, which increases and decreases depending on its function, is visible through the color coding. Mass is then generated through a sequential iterative process of coordinating the curves and the colors to voxels. As the voxels reduce in size and the volume is subdivided, the resolution of the building assets defines itself in order to find the configuration that maintains a monolithic quality whilst maximizing the surface area.
To evaluate the building assets' properties and potentials, we fabricated at a 1-to-1 scale. Here you can see two that were fabricated. The darker one is intended to extend from the internal to the external spaces, and the lighter is purely for the external environment. The varying colors are created by different binding agents that solidifies the mass, and the original prototype has a weight of 13 kilograms, which is the darker piece, and is roughly the size of 9 typical clay bricks. Therefore, its volume to mass ratio is significantly lower than that of an original clay brick. This is due to its materiality, which you may have noticed is sand, a material often overlooked in the building industry. However, its potential is greatly improved when it is 3D printed. It can endure up to 300 times its own weight and offers an improved precision. It also happens to be the fastest additive manufacturing technique currently available. This means that production from digital design to on-site construction can take as little as a few days. Not only can higher complexity be achieved, allowing the material and the form to work in synchronization, but the material can also be locally sourced and sustainably mined, making it economically efficient and massively reducing its carbon footprint.
3D sand prints exhibit unique thermal properties. This is why it's commonly used for steel casting. The material can absorb and store heat, helping to regulate indoor temperatures by reducing fluctuations. The structure allows for slow heat transfer, meaning they can hold onto heat during the day and release it at night, enhancing the comfort. By moderating temperature changes, they can reduce the need for heating and cooling, contributing to energy efficient in buildings.
To assess the potential of this monolithic 3D printed acid and its capability of reducing over-engineering in facade walls, we conducted an experiment focusing on thermal properties of sand and its compliance with building standards. So we tested the U value of the sand prototype against the clay brick wall as a control, with each experiment lasting about 72 hours, which is the typical amount of time that you need to run this test for. The interior of the experiment wall was heated to 40 degrees in a sealed chamber, which you can see is this red box on the right of the diagram. Yep. And thermal and humidity data was recorded using cameras and sensors. So these are thermal images of 4-hour intervals during the experiment. They illustrate how the building acid actually absorbed the heat but dissipated it very slowly through its mass, reducing its temperature by more than 20 degrees from the internal to the external surface. In comparison, the images show how the heat was quickly diffused through the clay brick wall into the air on the exterior. So these are visible in the temperature recordings as well, as the U value was calculated using at 1.4 without additional insulation. It therefore massively outperformed the clay brick wall, which was or had a value of 3.8. Visualized in this graph is the recorded U value and the wall thickness compared to the norms and their thicknesses when attempting to achieve a U value of 0.15. This shows that the material and the geometrical concept were both successful in achieving a value that exceeds that of existing construction materials and in achieving a lower value than that of the clay brick wall. We calculated the thermal conductivity using the experiment results and along with pre-recorded data to see how this corresponds to other materials within the building industry. It revealed that sand acid is situated somewhere between plasterboard and timber, illustrating that it has the potential to be used as a building material. So with more testing and iterations of the form and the thickness of the acid, it could potentially surpass thermal capabilities of materials currently used.
Like most designers, architects, and engineers, we are geared to making space and structure that not only accommodates for now, but creates a livable future. Therefore, we've developed an implementation method that not only relies on entirely custom-made solutions, but also relies on climate data itself. We will showcase this method on a typical Gründerzeit wall build-up. The surface area for the intervention to take place within is determined by a specific ratio of new and old. The percentage of new assets used across the facades are roughly 50% and focused on where there's a majority of sunlight and decay on the existing. The located bricks are removed from the existing wall, both interior and exterior, and the designed building assets slot in. This becomes seamless due to computational fabrication and accuracy. The colors indicating different applications of the surfaces. Green indicates only assets attached to the outer facade, blue to assets that span the entire width of the wall, and red to illustrate interior electrical routing and acoustic diffractions, relating back to procedural workflow of the individual asset. The use of biomaterials that mimics the surface conditions of cliffs encourage nature to reclaim space and unseal the facade. The asset provides room for animals, with the intent that wildlife that has been cast away from the cities, the human occupation, can now find residence here again. these protruding forms also self-shade the facade in summer to reduce heat gain.
So the assembly is designed with the capability to expand and retract so that they can adapt to any use case scenario, meaning the depth, width, and height are all adjustable. We call this type of implementation the buildalized approach, which means the fabrication occurs only when there is demand, preventing excess production and material overuse. So the project aims to combine computational workflows, additive manufacturing, and alternative materials to inform a site-specific, dynamic, and adaptive building typology, which has a strong and unique identity. If integrated into the urban fabric, we expect it to help cool cities affordably, with less impact on the environment. It's also contextually sensitive and is less carbon intensive.
The interior aesthetics harmonize with the exterior, promoting natural ventilation and indoor dehumidification thanks to the silica in the sand. This approach reimagines residential interiors, offering a tactile and haptical surface that challenges the traditional concept of stagnant white walls. To conclude, behavioral skins look to disrupt the building industry through sustainable, cost-efficient, and innovative design and construction solutions, ultimately to create livable environments on our planet for future generations by using natural and local resources to do so, embracing the philosophy that the best kind of building is no new building at all. Thanks so much.